Good morning, good afternoon, good evening, everyone. Welcome to this session. Thank you for joining us today. We are looking forward to a productive and engaging session. Our speaker here is the eminent Dr. David Smith. He's a principal AI engineer at Aveva. He has a doctorate in experimental fluid mechanics from the Imperial College of London. And he certainly is showing his intellectual fluidity by switching over to AI, I think, yeah? He will be speaking about deep reinforcement learning for autonomous manufacturing operations. What that means is he'll be talking about how deep reinforcement learning agents infused with AI are helping transition traditional industrial automation to industrial autonomy for core control, field, and production processes. So quite a profound topic again. But before we dive into content, just a quick guideline on how we operate this. So speaker will be talking for about 15 minutes. We'll reserve the last 5 minutes for Q&A. So feel free to post your questions on the Q&A tab of your Zoom chat. And then we'll handle questions as soon as we get to that session. So over to you, David.
Great. Thank you. Thank you very much, Anand, and good evening, everyone. It's a pleasure to be able to present to you on this topic of deep reinforcement learning. And I'm very grateful for the invitation from XLM today. Just to introduce myself briefly then, I'm David Smith. I work for Aveva in our AI team, and we're responsible for the application of AI technologies across our industrial software products. And the piece of work that I'm presenting today is something that we've partnered with NVIDIA for, which I'll explain a little bit further in the presentation. Click on. So just a few words about who is Aveva. So we're a world leader in industrial software. Our roots go back to the late 1960s in Cambridge in the UK, where we're still headquartered to this day. The company first pioneered and started life with 3D CAD technology. We were one of the first companies in 3D CAD technology for design, engineering design. And now our portfolio covers products throughout the design, operate, and optimize life cycle of industrial plants. We recently merged with another software company that you may have heard of called OSI Soft, and that's bringing then together the world-leading operational data management of the Pi system, which I'm sure people will have heard of, together with the rest of our industrial software portfolio. And in 2023, we became 100% owned by Schneider Electric. But our software products are agnostic. The software works with all our customers' assets and systems, no matter who the original manufacturer. We've got a very strong, as you might expect, emphasis on R&D and development, investing 175 million pounds each year in R&D, and that's executed by more than 2,000 staff across 10 locations worldwide. Just a little word about our partnership with NVIDIA. We're collaborating on a few areas, for example, creating high fidelity digital twins in our engineering design software. Schneider Electric, parent company, is working heavily with NVIDIA to create reference designs for data centers. But what we're talking about here today is our work on autonomous AI agents for control of complicated production processes. So what's our vision? What is autonomous operations about? What's our vision for autonomous operations, and why is it important to industrial and manufacturing operations? Well, for example, we can use autonomous technology, we can improve safety, we've got a greater level of surveillance of our operations, our equipment condition, abnormal situations using predictive maintenance, for example, early detection of issues. That means we're exposing field workers to hazardous situations less often. And when we do, those interventions are better planned with less firefighting. We can improve, of course, we can improve the efficiency and reduce costs of our operations. Digital twins constantly optimizing production processes, the utilization of our assets based on accurate monitoring of condition. We can ensure the best utilization of our resources. On sustainability, rather than retrofitting sustainability to our plants, we can build it into the DNA of our operations so that the control systems drive to optimize the sustainability impact of those operations. Most important, we can scale and connect data, feeding data, accessing data, connecting knowledge and insights in that data using language models, for example, that allows us to have real-time control and access to data across our operations and multiple sites. And that would have been inconceivable, even 10 years ago. And last but not least, and where we're going to focus our attention here in this presentation, is how we use AI to improve decision making, how we can make faster, more accurate decisions in the control, production, and maintenance of our plants using AI. So here we're talking about reaching higher levels of autonomous operations maturity, and that requires a blend of many technologies to transition from what we would call traditional industrial automation to industrial autonomy. And we can define three axes of autonomy in our operations. So first of all, how do I control more autonomously so that the combination of my operators and control systems make better decisions, requiring fewer manual interventions, and they're capable of driving the plant through a wide range of scenarios, maintaining product quality in our production. How do I conduct my field operations? So my maintenance with greater autonomy to plan and reduce those field interventions, as we just discussed, to improve safety, optimize the cost of our maintenance. How do I plan my actual production more autonomously, allowing more flexibility to make the most of the prevailing market boundary conditions, not just on a monthly or weekly basis, but in some situations down to days, hours, and even minutes. So in this presentation, we're concentrating on one important enabling technology within the controls area. As we all appreciate, control systems have come a long way over many decades. Level 0 and 1 on this diagram, we used to have plants, some of which still operating, which were heavily dependent on manual operations, moving to automation, but still based on 100% human decisions. At level 2, we have traditional closed loop automation systems. We're all familiar with PID, closed loop control, which will perform discrete tasks to manage levels, pressures, or temperatures in our process. And that's great. And it allows the human operator to focus on making high level decisions. But those closed loop controllers don't necessarily work so well for many situations, transient situations, batch processes. So they still need close operator surveillance and intervention. Whether we're getting the most out of the plant is still 100% human decision task. How do we bring more advanced autonomy that starts to drive the plant to operate, to optimize its performance? At level 3, we've got more advanced control technologies like APC, advanced process control, real-time optimization. They're using more sophisticated mathematical techniques to drive particular objective functions, outcomes on the area of the plant, and those can be very effective. However, there are still gaps in their capability. They still require manual interventions, which means they don't achieve the full system level autonomy where the operator can observe while the control system is seamlessly making decisions through all the situations which might occur. So we believe that AI, and specifically deep reinforcement learning, is a promising technology that is very complementary to those other technologies I just mentioned, APC and RTO, and that allows us to transition to level 4 autonomy and ultimately beyond to full plant autonomy. So, how do we see reinforcement learning being a benefit? And here I'd like to use a driving analogy to think about the types of control problem. If I'm cruising on the highway, not much is changing in my environment. I've not got much traffic. Maybe the weather might change a little bit. There's some clouds up ahead, but the road is nice and straight, and there's a few slight bends to negotiate. So my goal is to reach my destination on time with the best fuel economy. And to do so, I'm going to make small changes to my speed and steering. I'm not going to change gears. If I'm in the UK, that is, with a manual car, and essentially I can treat that as a pseudo steady state problem. And in an industrial context, we've already got these good control technologies like APC and RTO that I can use to accomplish that type of goal. If I'm driving in the city, though, my goal is still to reach my destination on time. I'd still like to achieve good fuel economy, but now I'm much more concerned about avoiding hazards. My environment's very transient. I've got lots of disturbances, traffic, pedestrians, roadworks, traffic lights. In terms of control actions, I've now got to make much larger and more rapid changes to my steering, speed, and so on. So in the context of our industrial plant and manufacturing situations, these situations can be highly transient. They have disturbances like feed changes, batch processes where we need to manage a certain trajectory of temperatures and pressures. And our traditional controls technologies there, like PID controllers, APC and RTO, won't perform so well in those situations. So most often operators take manual control of the system. So this is where we believe deep reinforcement learning could be very promising as an AI technology, capable of making these complex decisions within these complicated environments and achieving better outcomes as a consequence. So how does this work? DRL is an AI technique which learns to make decisions or actions in an environment where it has to accomplish some goal. So taking a super simple example, let's say I've got a tank level control problem. My goal is to teach the reinforcement learning to manipulate the level control valve to maintain the tank level at the set point for lots of different changes in flow, let's say, coming into the tank. The RL takes an action in the environment, and then I wait to see what the result of that action is, and I sample the new state of the environment, and then I look to see, did I do a good thing or did I do a bad thing? Did I move closer to my desired level, or did I move further away from it? And I assign a reward or a penalty based on that. And just like a child learning to ride a bike, we need to keep repeating this process over and over again. And the training the training of the RL is to keep adjusting its policy, that is the sequence of control actions that it makes, to maximize the cumulative reward that it receives with the best set of possible control actions. So however, in this case, we've got some important differences to the child learning to ride the bike. We can accomplish the training safely offline. We can use our Aveva dynamic simulation, which is a rigorous dynamic process simulation of the plant, and we can match that very closely to the behavior of the real plant, and then the RL can learn in that environment, makes lots of mistakes, which we could never do on the real plant. Furthermore, we can scale the environments to speed up the training. We can have multiple parallel environments to gather learning experiences from simultaneously, which can dramatically speed up learning. And using Aveva dynamic simulation in parallel, we can generate the equivalent of a year's worth of real plant runtime, maybe in half a day. Once we've trained the policy, then, well, what type of things can we do to it? Maybe we want to stabilize a production process after an upset, like a feed change. We might want to reduce the time for complicated startup and shutdown processes. And another very appropriate use case here is to improve the control of batch processes, where the evolution of the process is a continuous transient. For example, managing temperatures and pressures through that batch process, which represents quite a difficult control problem. So let's look at the building blocks of this technology. First of all, the reinforcement learning technology from NVIDIA that we're using. They developed a reinforcement learning tool chain called Raptor, which they originally used to optimize the design of their GPU chips. In so doing, they built in a library of standard reinforcement learning algorithms like PPO, for example, proximal policy optimization, which we can use very well for our industrial control problems together with Aveva dynamic simulation. That Aveva dynamic simulation is a very powerful process simulation tool. We can build very accurate process dynamic digital replicas of the plant, and it represents the physical and the chemical behavior of the process components so that they can run in real time or faster to create that realistic simulation that we need to train the reinforcement learning. It's heavily used across a whole variety of process industries, from energy industries, chemicals, and including pharmaceuticals processes as well. So let's look at a real example to bring this to life. This is a distillation process, which I'm sure, I hope is familiar to people in the audience. This one is about hydrocarbons processing, but it could be any distillation process that we're looking at here. The distillation process can undergo lots of different operational phases. We could be running a steady state, in which case my PID controllers would work pretty well. Alternatively, we may have upsets or even interruptions to the feed coming into the column. And that's where the reinforcement learning controller could be very advantageous here in terms of managing the operation of that distillation column. So in this example here, I'm going to show you we're going to consider disturbances in the feed rate coming into the column. If we get swings in the feed, let's say 20% swing in the feed coming in the space of a couple of minutes, how can we manage that column system? So we need to define this as an RL problem. That means, first of all, we need to decide what goals or skills we need the RL to accomplish. So I want to keep the column bottom level within a certain range. I want to keep the reflux drum level here within a certain range. And I need to maintain my product quality split between my lighter components and heavier components. And that means I need the RL to learn to control the temperature in the column bottom as well. So those are the skills or goals that we want it to learn. Then we need to break the system down into action and state variables. So what's it going to manipulate? Well, it's going to manipulate the amount of heat input to the column that we have. It's going to manipulate how much liquid we're draining from the column bottom, and how much liquid that we are refluxing at the top. So we've got three controls that the RL is going to learn to manipulate. Meanwhile, we need to give it inputs. What's it going to be observing to learn from? And those are the levels, the reflux flow, the column bottom flow, and of course the temperature of the column bottom. So now we've thought that through as a reinforcement learning problem, now we can begin the training. So how do we accomplish the training? Well, first of all, we need to configure the simulator in our Aveva dynamic simulation. And then we need to connect that to the reinforcement learning toolchain, NVIDIA's technology. And as I mentioned a few moments ago, We aren't constrained just to use one simulator environment. The beauty of this approach is we can use many in parallel, running in containers, and that gives us flexibility to duplicate the number of environments we use to speed up the training. So now we can run the training, which is all orchestrated by the NVIDIA RL agent. And once the training is accomplished, then we can export that agent as a policy, which we can integrate within the facility control system, either as a closed loop or open loop controller. And there, Aveva and Schneider have more technology to be able to integrate that advanced closed loop controllers in the OT system of plants via standard OPC communication, for example. So how did the RL do? Here I'm playing an animation of the training as it progresses. Actually, I'm just going to switch back and start that again. So at the beginning, it does badly. It's flooding the column bottom level a lot of the time, but gradually what you can see as we gather more and more training experiences, it gets better and better. And actually we're bringing that column bottom level, the reflux drum level, and the column bottom temperature into the desirable range that we wanted to achieve. And that took about 300,000 state action learning steps, which takes a few hours to run using multiple simulators. That was a relatively simple example. We're in the phase of conducting POCs and pilots for this technology with different customers, and we really want to put this technology into the real world. We already had one success story here with the Shell at their plant at Scotford in Canada, and this was about managing transient processes associated with plant trips. To be able to improve the robustness of their plant system, decrease the energy consumption, and decrease the restart time of the plant. So, just in conclusion, then, as we discussed earlier in the presentation, our autonomous plant has many aspects, and we can use AI technology which will make those more attainable. The use of reinforcement learning for advanced control beyond capabilities of today's control systems is one enabling technology to accelerate this. What's our next steps? We want to collaborate with customers to put this technology to use on real world problems. We're working on that now. Moreover, we want to get this out of the lab and be able to put it into the customer's own hands. That means we need to productize it. We need to speed it up. We need to be able to scale it so that customers can train their own agents. I think at that point I will close. But thank you everyone for your attention, and be very happy to take any questions.
Dr. David, there's a question. So what you just explained, right? Can you just walk us through a timeline, like from day one to getting some good results in the simulation, and actually implementing it in the real world? Just approximate timeline.
I think Nagesh, we're talking about, it depends on the complexity of the process and the amount of training that we do. But I think for the type of pilots and POCs that we're talking about, we're discussing now, that timeline can be sort of between 3 and 6 months to define the problem, build the simulation, conduct the training, and have an agent ready to deploy. Obviously, our goal is to shorten that timeline, dramatically in the future. But that's probably realistic for our current state with this technology. Yeah.
The next question for you. regarding efficiencies, right? This does require good technology, good software, right? And a good skill set also, people who understand all this and to train it and all that, right? So is it really viable for, I would say, small to mid companies, or are we focused only on large scale oil and gas, ONG, big facilities,
No, I think it is viable, Nagesh, because I think the most important thing is not, not the data science of the AI and the reinforcement learning. I think the most important thing is the subject matter expertise of the process, right? And how the process works, how to control that process well. That's really the most important thing. And it doesn't matter, what scale of operation we're talking about. I think the companies will always have those SMEs that are able to apply their knowledge, right?
So, one more question for you. So let's say we have good SMEs scientists who understand the process scientists. Then can we rely on Aveva to provide full support in terms of putting the hardware, the software in, but the subject matter expertise will come from the client, the customer?
Yes, that's correct. That's correct. Yeah, that's correct.
There's a question here which I will take, if you don't mind, Dr. David. It is, please, how do we go about GAMP validating these solutions? Very, very good point. And David and I have discussed this before also. So in my opinion, this can actually validate a process to a large extent offline. If you can show that the simulation bench is equivalent to the actual equipment, that is the key part, right? Like if I can trust the simulation bench with all the training and everything, is how close is it to my process? Then I can leverage this to do some testing, some experimentation. If you just use it for research, validation is not an issue, right? You're just doing it for research, to learning it, it's like a pilot. Then maybe I will actually use the parameters in the actual process. Then I will validate that one, right? So this will enable me to get to a validated state faster. But that's not the best use of this. The best use of this is, can I have a digital twin, right? So, and I need to validate that. So you need to take, again, the validation step, saying a known upset is introduced. We know how an actual system will react. Now let's do the same series of upsets, like, to your simulated bench. What kind of an output am I getting? Is it close enough to what I would expect in a physical system? Because I already know how the physical system reacted. Now I need to know how your bench reacted, just to establish that equivalency, right? Then I can say, yeah, it is working nicely. Then maybe I can call it validated. Then I can use this as a validated test bench to accelerate some of my process development. Am I correct, Dr. David?
Yeah, absolutely. Yeah.
With this, Dr. David, I don't know how to thank you. It's so late in the UK right now. I really, really appreciate it.
That's a pleasure. Yeah,
a pleasure. Something like this is not commonly discussed. Like what you are just talked about in 20 minutes, it's not discussed heavily in life sciences in terms of establishing a digital twin, establishing a reinforced learning data bench or a simulation bench with dynamic simulation. One thing you didn't touch upon in detail was the chemical properties themselves. That's what Aveva is an expert in, correct? Can you just quickly touch upon that, please?
Good point. I mean, we've got a huge library of thermodynamic properties data behind our simulation tools. And in fact, we're even working on other application of AI technologies to predict properties for for molecules that aren't in that data. So yeah, there's a lot of knowledge and work behind that. Yeah.
So basically, just to rephrase what you just said, just for the convenience of the audience here. So you have a good library. So let's say I'm using certain chemicals in my process, and you already have modeled that in your library. So
yeah,
make it much faster, right? You can predict how the molecules will behave, based on certain parameters, pressure, temperature, whatever that is, right?
Right.
Okay, that's exactly wanted to confirm that. Dr. David, again, thank you again. Have a good night.
Thank you. That's a pleasure.
Thank you.
Thank you, all the participants.
Yeah, thank you.